Okay, everybody, welcome to my talk. My name is Untitled. I'm working for the company Fortis, and I'm talking today a little bit about something up to now completely different. It's about industrial automation. And what we did with this, it's called FODIAC, Framework for Distributed Industrial Automation and Control. This already says it in the title. So we are doing something industrial automation. Something a little bit, but I want to give you a little background what industrial automation is all about, why I think it's different, or why others think it's different, or on the other side, why it's the same. So I think the talk into the M2M topic, because industrial automation is about machines. Heavy machines, big machines, or even sometimes also small machines, but most of all it's about metal. Moving metal fast and accurate. And on the other side, these machines have to be very sensible, producing fine things and interacting with each other. And here comes the M2M, so we need machines that interact with each other. I will introduce a new paradigm for programming such machine. It's called IC 61199, which is a standard about how to do this. Give an application example, how 4099 applications look like, and then I will go into FODIAC, why we are, what we did, and how it is supporting all the other things. So, industrial automation is in principle about embedded systems. So, last talk we talked about automotive systems, aerospace systems. In principle, we are embedded systems. We have some computers that are put into these machines that are controlling these machines. We have sensors, we have actuators, we have safety, we have accuracy, we have real time. So not really different from what you would expect from an embedded systems application development point of view. What is really different is that typically our machines are one of a kind. It's very seldom that the same machine is produced or is built in the same way many times. There are machines that have some only variabilities, but if you're looking at the plant automation, manufacturing automation, like car manufacturing lines, mobile phone assembly lines is a very good example. These are one of a kind. They are designed for the product to be built. And that makes it very different. So we are not able to design our embedded system specifically for this embedded machine. We need something more generic. We need something that's applicable to all the different machines. And this is where this special hardware comes into place, which is called PLCs, which has been invented somewhere in the 70s, introducing computers into the industrial automation. We've seen something like this yesterday when we were enlightened a little bit about Industry 4.0. On the other side, we have also another problem. We have personnel maintaining these machines that have very low programming skills. So people that are operating the plant and the plant stops operating. Something is wrong, maybe a pump is broken or some piston is not moving anymore. What's all about is that somehow parts are not coming out of the machine. And the poor guys that are sitting by the machines are paid that as soon as possible parts are coming out of the machine again. So these guys have to find out what's wrong, how to fix it, if it's maybe a programming error, if it's a sensor error, maybe a cable is broken, and they have to find means to do this. And with not very much computer skills. We always talk about the guy with the hammer and on the other hand the screwdriver, running around and trying to fix things. This is maybe a little bit exaggerated, but in principle this is where it's going. Therefore, special hardware has been developed, special domain-specific programming language has been developed, also dedicated execution models to simplify all this task, so that we don't have to rethink all the stuff about it again. On the other side, we have new demands now coming up. Product life cycles are drastically decreasing. Look about mobile phones. So every half year or fast, a new mobile phone is produced. Car manufacturer, volumes going down, variants going up. And these are things, so our production system have to be flexible, adaptive, very often, even machines that producing high volume in short amount of times have to be capable of changing the products during the lifetime of the machine, or even have to be designed to have many different products from the beginning on, because one kind of product or one variant is not sold in such a high volume that the machine would be efficient. So these are the things that are coming to mind, and this brings us to Industry 4.0, which we have seen yesterday. So we need machines that are connected, they are somehow maybe self-aware, so that they find errors, they are maybe responsive to their operators, responsive to the products they are manufacturing, and self-adjusting or adjusting to these different needs. And this requires for new architectures and programming models, and this is not really new. So when I've seen the first time Industry 4.0 and what it is all about, I thought, oh fine, we are doing this since 20 years now. So I'm a researcher. I'm researching industrial automation since about 2000, 2002. Since 1990, we have ideas around that says we need more flexible adaptive production systems, agile production systems, self-adaptive systems. There is a key topic called holonic manufacturing systems, something about swarms and self-aware machines that will organize themselves by interacting, sending emails to each other, negotiating production flow, negotiating who will produce what product or what part of the product. And from that already it originates that PLC programming as we know it, and as it's still used, so this hasn't changed much, is not capable to fulfill all these requirements. And therefore, the new paradigm has been developed. It has been developed more than 15 years. So the first version of this IEC 61499 standard was presented in 2005, and it tries to put in better or improve the existing, or at that time existing way of programming PLCs in order to be more distributed, so that we can have distributed control devices that each interact with their part of the machine, negotiating with each other, that we have adaptability, reconfigurability already designed into the programming language. Yeah, this is more for people in the domain. So, but the core point about 4099 is the so-called function block. You would say component, I think, or maybe a very small component. It really depends on what how much functionality you put into it. Before 4099, what we had is also function blocks, but only function blocks with data interfaces. So we have this Simulink-like data flow languages where you have data input coming into the function block, will be processed, produce data output. And magically around the system where this function block is put into will ensure that the data is provided, that the function block is executed in time, and that output data is given to the next things. Typically it is done in a cyclically way, because then we know all about the real-time stuff, and yeah, this is how it has been done. What 4099 added is this head on the top above, is to add event connections. These event connections allow now that this to trigger actively these function blocks, to synchronize function blocks, for example, with the network, or actively produce messages on the network. So especially for the distribution, this event mechanism is very helpful to synchronize and send messages along distributed devices. So this was already the first point why we need these events. The second point is that now you have active control about the control algorithms. So you are in charge of which function block to activate at which time, and within the function block you can decide what to do with the events and the data. And this gives the programmer more empowerment, makes the control application more independent from the control device, because before that it was a configuration of the device how it was done. Another thing that may sound for Java programmers or for software developers rather ridiculous, we had very strong relied on global variables before that standard. So this has all been removed, so that we really have a software component without hidden interfaces. Only the internal stuff can so what is hidden in the function block can only access the interfaces can be tested independently, can be deployed independently, and when connected to other function block will not change its functionality, which is very important. But I don't think I have to tell you this. Yeah, and then there are special function blocks for accessing the hardware, which is also important. So everything in 4099 looks like this function block. And this makes it sometimes a little hard to understand the different models. But in the end, it's also very intuitive, because if you see a function block, you know what you can do with it. Just connect the lines and use it. Yeah, so as you have guessed from my last sentence, building applications now is something graphical. You choose your function blocks. Hopefully somebody else has already developed for you. Connected with event connections, connected with data connections, and here you are. Function blocks and our applications, which is very important, are developed independent from the system, or well, not from the system, but from the system configuration, which hard control devices are really available. So you can here really develop your logical function. You can say, I want to control a piston that will press a knob into a door or whatever. And this is my functionality. So I need maybe some PID controller for controlling the pressure of the piston. I need some sensors. I need some actuators for acting with the piston and stuff like this. But this already, if you have an appropriate environment, can be simulated and tested, and you can evaluate, is this the functionality you like to have? Which is also very important for industrial automation, where very often when you could be programming the system, the real system is not available, because this piston is about this size and it has to be manufactured, has to put in place, and it's maybe dangerous to operate it up front, so you have to perform a certain phase how to implement, or how to set it up and to get it running. In order to get now your application on real devices, the next step is to use the system model, where you have devices, and as we have a distributed system, we have a set of devices, and these devices are connected to a process. This is a very generic process, so this is nothing specific described in the standard, but only the devices have interaction with this process, our sensors and actuators. Some I/O modules or I/O that we have here. On the other side, we have communication infrastructure. We are a distributed system, we need to interact somehow. And then you can map your function blocks to the different devices. So in industrial automation, this is currently mainly a manual task, especially keeping in mind the operators, so that you know which functionality has to be put into what device. So especially for maintenance purposes, getting plants up and running, keeping it up and running. Another point that is also interesting is, if you put now these function blocks, as I did in different devices, we have now the problem that several connections are now broken. If you look, for example, where's my mouse, the connections here between function block 1 and 2, they are a set of event and data lines. And this means that you have to put here some, currently manual, I hope you can in the future also do this automatically. In the devices you have to then program some platform specific stuff. Still, this will not change the functionality of your overall application. It's just glue code, I would say, or platform specific code that has to be done. You can also have several applications in your device. This is often very interesting if you think that this is maybe some firmware functionality. Maybe if this is a pump, then this may be the closed loop control providing the pump speed or the pump throughput, and this can be then used by a coordinating control application that will then coordinate the overall stuff that's needed. Okay, to get this a little bit more graspable, I have brought a small control example with me. I don't know if anybody of you is familiar with this schematic drawing. This is a very typical drawing used in process industries. This U is a tank. In this tank you can fill via this valve some liquid. This sensor here detects the filling level of the tank, and here we have a pump that can be put to a certain revolution to draw this liquid out of the tank. What we like to do is that with this stuff above here is to control the valve for a certain height to maintain a certain height in this tank. And someone else is taking liquid because it's maybe needed for the process, but we don't know how much, so this is like a disturbance to our control algorithm. In addition, we would like to have some simple HMI, maybe for setting the set point, doing hand automatic control stuff like this. Yeah, the application, first, not to forget, this example is an extended and reworked example from James Christensen, who is the chair of the IEC 1499 working group. And I took some function blocks he developed some years ago. So what I have here, the main thing is here in the middle. This is a PID control function block that will get the current level of the tank. It will get a set point from an HMI and tries to control the feed, the pump speed in order to maintain a certain tank level. So this function block, it's called tank model, simulates our tank. Here we have some view that will show us the tank afterwards. Here we have a function block that will present us a strip chart, but it's easier if I show it like that. And if you run this in my simulator, it will look like this. So here this is the faceplate HMI, so I can here say I want hand automatic mode, a set point for which tank level I would like to have. Then, yeah, this is the current process value of the tank, and this is the output of the valve. So the side, the volume of the valve. And yeah, here you see the scripture, how this will look like. The only thing is I forgot to match the colors, sorry for that. So the red line is the yellow here. So this is what I would like to have as a set point. You see here the motion of the valve, so how, if it's opening or closing. And the yellow one is the current value of the tank. You see here, this is already quite good. We have here some small error, so maybe I have to adjust the PID the parameters of my PID control a little bit more. But for the first set, it's quite okay. So it's working. It's not like exaggerating. We have no overflow of the tank. Oh, that's fine. So in the next step, we can model our system. So in this case, I dedicated a device for the HMI. I dedicated a device for the controller, and for the simulation, I dedicated a third device. And now I can say, okay, assign my function blocks to the different devices. You already see I have done this for all these function blocks because now they have a color. So they match the color of the devices here. And you also see here we have these dashed lines, which means these are connections that are now broken. So these are connections that are going over the network. And this is the next step what we need to do is to add additional function blocks, the white function blocks you see here. So you get different function blocks for getting and also receiving and sending the values. For example, here I had to add an additional function block for adjusting values because they were not received in the right range, which was in the central application not needed because in the central application this is this one. So I cannot use it double. I cannot use it doubly. So yeah. And when I run this, I only can run it in simulation, but then I get three separated devices which will then interact via communication. Okay, and what you've seen here with these screenshots already has been with our tool 40ec. So this should be, so far it was just an overview what 1499 is about, what 1499 can achieve. And at the time when we started all this research, it's a little way back, I think 2002 or so, there were already some 1499 implementations available, nothing commercial, only one free non-open source tool, and this tool was, let's say, rather crappy. And we started then research projects funded by the Austrian government. At the time I was in Vienna, and we had to restart all projects from the beginning and from scratch, because then there was a company owning the rights, or different people were working together in getting the things up, and so it's very hard to reuse our research results over different research projects. And at the end of one of these research projects, where we developed the runtime environment for 4099, we finally could convince our partners it would make sense how much would we have achieved more if we would have open sourced from the beginning, or if we would have already had this open source core platform. And from this on, we started to get our platforms open source. We started with our tool. We got our tool open source. We got the runtime open source. This was our initial contribution, especially to foster this development of 4099, and also to leverage a little bit research and industrial adoption of IC6 on 4099. In the meantime, this is now nearly 6 years that we are publicly available as open source project. We started with the IDE, which is EclipseCon, as you may have guessed. Then a runtime environment Forte, which is C++ based. We added now libraries so that that you can easily make such applications as I've shown you without the need to develop your own function blocks. And our youngest and smallest sub-project, some example applications, so that people can just start and see how this thing is working. Yeah, we are Eclipse public license, and what I want to point out, which is really important, but was also important for our customers from the beginning, is that it allows you to add on and build on products. I think this is very important, and also for the Eclipse environment. What I also wanted to point out is the industrial users. We started as some crazy researchers in a small country like Austria, where we just had some tools, environment, and thought, yeah, let's put it open source. In the meantime, some companies took it over, or took on it. For example, the company NextControl, their control devices are really based on our C++ or runtime environment. They did an own tool, because this was their business model. On the other side, ABB, for example, is using our tool in order to generate code, because for them it's much easier than to develop an own tool. So this is how the different use cases are done. And what I'm also very proud of, that all over the world, universities are taking, in the industrial automation world, are taking it up and using it for teaching, for researching, and different ways of using 4099. To give you an overview where it's used, building automation is a very strong domain of 4099, where you have lots of devices, you have lots of communicating devices, process industries, laboratory automation. Smart grids is also a topic, and classical machine control. So, to bore you a little further, I have some screenshots and show you a little bit what's all possible. What you've already seen is application development. You have already seen the detailed screenshots about modeling function blocks, about modeling applications, like you're doing here, modeling your systems, then configuring your devices. Yeah, these are all GF editors, which is like very nice, like getting an outline. Yeah, but also recently we adopted the CNF, which also helped us very much to manage our libraries. Yeah, but we have more. We have then also the function block development. Function blocks internally are also mainly modeled graphically. So you have the interface modeler up there. Depending on what's inside, you either have a state chart, you have other function blocks, or you have just such sequence diagrams. And for the state charts, we also have textual editors. So it's a full mixture of different editors that are working together, partly working on the same models, working on different models. Keeping this all up and synchronized gives us sometimes a little headache. Yeah, I really forgot this slide. What's also very important this is a very recent feature, I think we just have it for half a year now, that we can now go online from the tool to our devices and say, I want to monitor this function block, give me how many events have been received, how many events have been sent, how are my data values, maybe trigger an event, so saying, okay, it could be a test if this functionality is working, or what's also very important, force a value. very often maybe a part of the system is not available or produces for your test not the correct results. So you need to set it to a fixed value which is not changing during execution, which is in industrial automation called forcing. Yeah. For industrial automation, a typical feature, we are very happy that we have it. It cost us quite some implementation effort. So on the other side, we have Forte as our main part. It's the runtime environment that builds the basic infrastructure for executing our 4099 applications. In principle, it provides all the core functionalities that are required to execute 4099, interacts with the tool so that we can download applications. It's written in C++, very modular, so that we can scale it up from very small devices to rather big ones. And what's very important is also our communication infrastructure, so that we can easily add new protocols without making many changes with them. And we are real-time capable. If we have a real-time operating system that supports us, we can really do hard real-time execution of our applications. Where we are currently running, so officially supported devices, you can see here on the left side, you see a real PLC. This is an industrial controller. Some embedded devices like this DigiMe. This is an educational robot controller for a robot league in the States. And Lego Mindstorms, although Lego Mindstorms is our smallest platform, but also one of the hardest we currently support. We hope that we can improve this in the future. Yeah, and further tested and hopefully in the future upcoming. What I can say, I definitely, there are many people now working on Raspberry Pi, so this will be definitely, I say hopefully, but I guess it will be in the next release that we officially support. So as Raspberry Pi is Linux, it already compiles on Linux. The interesting part is that you already get libraries for accessing the IOs. And this is the most interesting point. So if you want to run it on Raspberry Pi, go ahead, compile it, it runs. So this is just our standard Linux code. Yeah, so how you would do this, what I've just told you. Currently, if you model something in your tool, one thing you have to know is that currently function blocks that you develop have to be compiled into the runtime environment. This is a little drawback because you have to rechange the flash file. So you take your function block, generate C++ code out of it, take the Forte with your target compiler, and you build something like the Forte. But the important thing is now, although you compile the Forte, you can download your applications, your connection information, your instance information from the tool, and you can change it dynamically. So once you have developed your function block, you have tested your function blocks, you can build different kind of applications with it without changing the target device. And hopefully, and this is something we are investigating currently, how we would do it, we want to also download the function block types, so that you can develop a function block type, download it to your device, and independent what kind of device it is, it will run and execute the same. So this is also a point that we are targeting, making a platform-independent way of accessing all the different devices that are lurking around in industrial automation. Okay, and with this last slide, I want to give you a little impression of where we, the core team members, already tested and used 40X. So you see things like inverted pendulum, the classical for teaching closed-loop control. Here some inter-process logistics system. It doesn't look so big, but it has about 120 control devices. So there we're really investigating highly distributed control. On top, this is one of our biggest applications with the most function blocks. There are about 1,000 or 2,000 function blocks in several hierarchy levels in one application. And these applications are very interesting. There, 40X is used not as real-time control environment, therefore it's used as sequencing and coordination environment. There we have 3D scanners, cameras, industrial robots, grippers, humans, mobile platforms, and these are coordinated. So this is a bin picking application where a 3D scanner checks how the parts are lying in the bin, calculate, another system is then taking the 3D information from the 3D cloud, calculating which parts are lying on top of each other, which one can be grasped next. And this information from this is then a path calculated for the robot, and the robot then can pick it and put it on a conveyor belt and put it on, give it a liquid into the hand or so. And there, this is really the biggest one. From the function block point of view, from the application size and from the physical size, this thing is the biggest. It's called Smartest Lab. It is in Vienna. From the Austrian Institute of Technology, and this is a smart grid test lab and an evaluation lab for PV inverters. Every PV inverter, so if you put the PV plates on your roof of your house, the inverter, which then makes the current for your connectors, needs to be tested if it fulfills certain regulations, and these regulations are typically very specific to the country or even to your grid provider. So, and this is one of the labs in Austria where such PV inverters are tested. It has been opened in April. No, yeah, it was in April. May. It's pretty big. It has more than 1,500 I/O points. This goes from measurement devices like current measuring, power measuring, voltage measuring, then lots of switches and sensors. Because what you see up in this racks and in this racks, what you see here are lots of resistors that can be turned on and off. And for this you can set certain set points and test certain things. And 4099 or 40X is used here for allowing users to perform these actions, and on the other side making it safe, because certain switches may not be turned on and off while others are turned on or off. And this has been then connected to an open source SCADA system, which is called SCADA VR for SCADA Brasilia, which is a quite nice web-based SCADA system. And there they're also doing other things. So we have a broadband from very small, this is just one device, and we have 2 sensors and 1 actuator. So this is, I think, the smallest, but with the highest real-time constraints, because if you're not very accurate, this is about balancing your pendulum. The pendulum will fall down, or the carriage will move as crazy as possible. I've done this, so I know how it's working. Till very many function blocks, till very high, big systems. What I forgot to say, this is also dangerous. We have 65 kilowatts of power running through this. So these are big cables. Okay, thanks for being here today. I hope you enjoyed it, and here you can find 48.
What communication protocol do you use to establish communication between the function deployed on the many devices?
Currently we are using a protocol, we are using Ethernet, and they are UDP or TCP, and on top of that an ASN1 encoding, which is defined by the standard itself. But I've shown here, we also try, we have a Modbus, so with currently on the client, so you can have Modbus slave devices where you can acquire data. We have OPC there where you can acquire data, which is, and if you need another protocol, it should be rather easy. It's about 1 or 2 classes, depending on the protocol, which you need to implement by yourself.
And up this layer, you implement something like OSGI remote services?
Could be possible. This is something that you can, what's very, could be interesting, maybe not OSGI, but other services to implement, saying there are certain features in 4099 which I could not present today because of the time, which could easily allow you to define interfaces to the network, like service kind of interface, and which could then be invoked by others, especially for saying I want to coordinate a set of machines. There are many standards out there, like the IEC 61850, which is here for smart grids, or OPC-UA, or other service kind mechanisms that define how the interface of such a device should look like, but nobody is talking about how to implement them. This could be an option for implementing it in an industrial kind of way.
You were talking in this plant that there is a lot of power, so it's dangerous. So how your tool is qualified to produce proper C++ to implement in your... is it qualified or...
No, it's not qualified. In this case, it's an test lab and it's a research lab, therefore it's not such critical. In addition, there are power protective system applied, which will anyhow...
You take the risk. Only researchers.
Yeah, it's only researchers. No, it's a good friend of mine who's doing this, so I don't want to have him replaced. But he knows what he's doing. And there, in addition, if you're taking about power systems, there are current protection systems, there are voltage protection systems. The only problem is that if a current protection system for 65 kilowatts has to turn on and turn off the current, I'm very bad in calculating how much ampere these are. Yeah, but these are 100 or more amperes, so this is pretty loud and it does cost something. So therefore it's quite good to have protection.
And concerning qualification, do you plan to qualify your tool or the code generator or this kind of thing for the future? Or in automation, there is sometimes big machines that need security or reliability on the code that runs.
That's definitely an interesting point. One of the companies which are using it, Dex Control, is operating pretty heavy machines with it for several years now without problems. So I'm pretty confident in the code. Nonetheless, as we are, this is a research organization, we are using this as platform for doing our research.
Okay.
So we are not in the position of doing this because we don't have the resources and the money for doing this. If somebody is interested in doing that way, I'm happy to support this. Definitely.
Okay. That's okay.
Yeah, it might actually be up to the industry to step up and do this type of qualification.
Well, you said ABB Research. I think those guys have a few dollars here or there.
I don't know. I just they are using the tool mainly in generating own code for their platforms, which is also another option. Which is a point which I haven't talked about because I'm not. What I also forgot to tell: the original tool since 2 years ago was maintained and developed by one guy. So all the editors you see, all the models behind was one guy. In part-time, besides the other research projects he was doing. And I think this really speaks for all the Eclipse things. And we were not even using all the things that were available because we were not aware about them. Like adding the CNF, what I did, really reduced our code base and helped us to get some things more stable. So this is really to speak about how Eclipse can help you. And with all the lots of plugins and the flexible plugin structure, you can easily say, okay, the tool is nice, but I need a certified code generator. Okay, there is a certain place where you can plug in another code generator. Be my guest.
Another question. Inside the functional block, is it possible in your tool to write the inside directly in C++ or in C or language?
No, this
I don't know if somebody wants to go for lunch, otherwise I can talk for hours on this topic. The classical function block looks a little bit like this. So you have on top here the so-called execution control chart, which is a state machine. The state machine is a little bit special as actions are only triggered on state entry. So you don't have any other actions like transition actions, leave actions, only state entry actions. The conditions are either event and some condition, just an event, just a condition. So this is what, there you can already express lots of your logic. So especially, I'm unfortunately doing not so much 4099 development anymore, but there you can really express lots of your logic. So, and what's not possible to represent here, you can then put into algorithms, and algorithms can be written in principle in any language you like.
Okay.
So this is what the standard says. On the other side are, in order to support you, in order to make the tool a little bit more manageable, we are currently encouraging you to use 1131 part 3 structured text, which is in Pascal modular 2 Ada-like language. So you have whiles, you have for loops, you have if then else, switch cases and stuff like this. And this we all bunch together, and from this we make C++ code. And this makes also our code generation rather easy. Because the interface, these are just some data files, some arrays with parameters, and the hard part is only the algorithms here.
Okay.
So therefore I'm pretty confident in our C++ generation. On the other side, who knows?
But you do have editors for this specific language, what you...
Currently it's a pure text editor. We are looking at to making it some more a cooler editor. Like I've looked a little bit in Xtext, but the problem with Xtext I had is the algorithm is somewhere hidden deep within an XML file. And so getting there an appropriate model and getting this out into the editor and back into the model, this was for me too much, but I'm a C++ programmer, I have to confess. So I'm more the I'm the runtime guy here. I'm maintaining small bugs in the tool, but I'm the runtime guy. Or I also had a look on EMF text. We have already models for the language. So if anybody steps up, I give him the model and he integrates it in the editor, I'm happy. I also heard that one of my colleagues had tried for, because we can also use C++ in the editors, that he used the syntax highlighting from C++ in the editor. I don't know if you can see it. It would. This editor looks a little bit like this. So you have here your algorithms, and then here is the classic Eclipse text editor. So it's already the text editing framework. You just have to provide me the class with the formatting stuff, and I'm happy. This is at least what I tried. And here you see also a little bit about structured text, so this is, yeah, more or less what's going on here.